February 8, 1942. Jakarta Airfield, Java. The Boeing B-17E Flying Fortress serial number 41 to 2471 lay abandoned on the tropical airfield, its American crew having fled the advancing Japanese forces just hours earlier. The aircraft belonged to the 7th Bomb Group of the United States Army Air Forces. And although damaged in a crash landing, it remained largely intact. Within days, Japanese forces would discover this bomber and others like it scattered across Java's captured airfields. What they would learn from examining these aircraft would fundamentally challenge their understanding of American industrial capability. The aircraft represented more than just military hardware. It embodied an entire philosophy of manufacturing that stood in stark contrast to Japanese production methods. Over the next 3 years, Japanese engineers would systematically examine captured B-7s, documenting every aspect of their construction. The conclusions they reached would prove devastating to Japanese confidence in their ability to match American industrial output. The discovery began in March 1942 as Japanese forces completed their conquest of the Dutch East Indies. At Myoan Field in Java, engineers found B-17E serial number 41 to 2471 in remarkably good condition despite missing its nose section and engines. At nearby airfields, additional B-7s awaited in various states of damage. Toro Saito, an aviation editor from Asahi Press who toured Java's captured bases immediately after the Japanese occupation, documented the discovery. He counted 4 B-17E being readied for evaluation, 1 at Malong, another at Cirebon, and 2 more at Bandung. The maintenance facilities for the B-7 in Java were excellent for that time and existing conditions. Saito later wrote, "It appeared that Bandung Field was the main maintenance base for the Americans, and it was here that Japanese technicians from the JICAN performed their initial evaluation." The JICAN, officially known as the Koku Jutsu Kanujo, or Air Technical Research Institute, represented the pinnacle of Japanese aeronautical engineering. Based at Tachikawa Airfield near Tokyo, this organization employed Japan's most advanced aircraft designers and engineers. When word reached Tokyo that intact B-17 bombers had been captured, the JICAN immediately dispatched technical teams to Java. The Japanese faced a significant challenge in preparing the captured aircraft for evaluation. The B-17E was the most advanced version American forces had deployed to the Pacific at that point in the war. Its systems were more complex than anything in the Japanese infantry. Using parts salvaged from multiple damaged B-7s and employing captured Allied mechanics who had been pressed into service, Japanese engineers began the painstaking work of restoring at least 2 B-17Es to flying condition. The work required months of effort. Engineers had to understand electrical systems, hydraulic systems, and engine installations that differed fundamentally from Japanese designs. They studied instruction manuals captured along with the aircraft, translating technical documentation and learning American engineering practices. By late 1942, Japanese engineers had successfully restored 2 B-17Es to airworthy condition. A third aircraft, AB-7D captured at Clark Field in the Philippines, had already been flown to Japan earlier in the year. The decision was made to transport the restored Java B-17Es to Japan for comprehensive evaluation. The flight required elaborate preparation. The route would take the bombers through Singapore and northward to Japan, a journey of thousands of miles over territories recently conquered by Japanese forces. Elaborate flight plans were prepared to prevent Japanese air defense forces from shooting down their own captured aircraft. Fighter escorts were assigned and a Nakajima L-2D transport, the license-built version of the Douglas DC-3, would accompany the bombers as a mothership. Every air defense unit along the route received advanced notification. In May or June 1943, the 2 B-17Es successfully arrived at Taishiwa Airfield near Tokyo. They joined the B-17D that had arrived earlier from the Philippines. Japanese engineers now possessed 3 examples of America's primary heavy bomber for detailed study. Major Kazuyuki Saitito of the Imperial Japanese Army Air Force headed the evaluation team at Tachikawa. An aeronautical engineer with extensive experience in aircraft design and testing. Saito assembled a team of specialists to conduct a comprehensive examination. His team included Lieutenant Shiyama, Lieutenant Secondas Kurusu and O'Hara, and Army Assistant Engineer Shimamura. Major Uno and Captain Yagi served as test pilots, while Army Engineer Kanio conducted detailed studies of the engines and propulsion systems. The team's assignment was clear. Document every aspect of the B-7's design, construction, and capabilities. Since the Japanese had also captured complete instruction manuals for the aircraft, no detail would be overlooked. Every system would be tested, every component examined, every manufacturing technique analyzed. The examination began with the airframe structure. Engineers carefully documented construction methods, measuring rivet spacing, panel thickness, and structural member dimensions. What they discovered immediately challenged assumptions about American manufacturing. The consistency of construction across all three captured aircraft proved remarkable. Rivet holes aligned precisely between different aircraft. Structural components appeared interchangeable. Panel forming showed identical characteristics across multiple examples. This was not the work of individual craftsmen adapting parts to fit specific aircraft. This was systematic mass production using standardized components manufactured to precise tolerances. Japanese aircraft production relied heavily on skilled workers who fitted components individually to each airframe. No two Japanese aircraft were truly identical. Parts from one aircraft often required adjustment before fitting another. Repairs in the field demanded skilled technicians who could modify replacement parts to match the specific aircraft being repaired. The American approach appeared fundamentally different. The B-17's construction suggested that any part manufactured to specification would fit any aircraft of the same model without adjustment. This level of standardization required manufacturing precision that Japanese factories had not achieved. The engines provided even more dramatic evidence of American mass production capability. The Wright R-1820 Cyclone radial engines powering the B-17 consisted of hundreds of precisely machined components. Engineers disassembled the engines completely, measuring clearances and tolerances throughout. What they found astonished them. Every component was machined to tolerances measured in thousandth of an inch. Crankshafts, connecting rods, cylinder barrels, pistons, all showed identical dimensions across different engines. The maintenance manuals confirmed what the physical examination suggested. American mechanics in the field were expected to replace major engine components without any fitting or adjustment. A cylinder from one engine would install directly into another engine. A crankshaft was a crankshaft precisely interchangeable with any other of the same model. This stood in stark contrast to Japanese engine production. Japanese aircraft engines required skilled assembly by experienced technicians. Components were often hand-fitted to achieve proper clearances. Field maintenance demanded highly trained mechanics who understood how to adjust and modify parts. The American system eliminated the need for such specialized skills by ensuring that precision was built into the manufacturing process itself. The hydraulic system demonstrated similar principles. Japanese engineers examined the actuators, valves, and control mechanisms throughout the aircraft. Fittings used standardized threads. Lines connected with identical couplings throughout the system. Any hydraulic component could be removed and replaced without modification. The electrical system showed even more sophisticated standardization. Every wire connection used machine-crimped terminals rather than hand-soldered joints. Wire gauges followed consistent standards throughout the aircraft. Circuit breakers, switches, and instruments appeared to be modular units designed for quick replacement. Japanese aircraft electrical systems typically required skilled electricians who could solder connections, adjust contacts, and troubleshoot complex wiring. The B-7's electrical system was designed so that a mechanic with basic training could replace entire assemblies using simple tools. The oxygen system for the crew included precision regulators controlling flow to each crew position. In Japanese aircraft, such regulators would be assembled by highly trained specialists. The B-17's regulators bore manufacturer stamps indicating they were produced by automobile parts suppliers, companies with no prior aircraft experience. This discovery carried profound implications. American industry possessed such depth that automobile parts manufacturers could produce precision aircraft components simply by applying their existing manufacturing capabilities to new products. The bomb release mechanisms told a similar story. Japanese bomb racks required careful adjustment by armament specialists. The B-7's bomb shackles were self-adjusting mechanical devices requiring no calibration. The defensive armament particularly impressed Japanese fighter pilots who flew practice intercepts against the captured bombers. 13 Browning M250 caliber machine guns provided overlapping fields of fire covering virtually every approach angle. Each gun could fire up to 600 rounds per minute. The guns themselves revealed another aspect of American design philosophy. Engineers examining the weapons found them surprisingly crude in construction, built to loose tolerances compared to Japanese aircraft guns. Yet, they functioned reliably despite what Japanese engineers considered rough manufacturing. The design achieved reliability through robust engineering rather than precision craftsmanship. Any competent armorer could maintain the weapons using simple tools and basic training. Japanese aircraft guns were precision instruments requiring skilled maintenance. American guns were robust mechanisms designed to function despite imperfect conditions. By autumn 1943, all three captured B-7s were flying regularly from Fusa Airfield near Tachikawa. Japanese pilots gained first-hand experience operating the heavy bombers. Test flights documented performance characteristics, handling qualities, and operational procedures. The aircraft appeared in Japanese military training films demonstrating combat tactics for intercepting American heavy bombers. Films showed Ki-43 and Ki-44 fighters practicing attacks against the captured B-17s. These films sometimes featured the B-17D repainted with American insignia, occasionally escorted by a captured Curtiss P-40 fighter for additional realism. The films played in Japanese public theaters as propaganda, showing Japanese fighters successfully engaging American bombers. What the propaganda films did not show was the sobering conclusion Japanese fighter pilots reached after extensive practice intercepts. Even when Japanese fighters successfully attacked the bomber, the B-17's defensive firepower and structural strength made it a formidable opponent. More disturbing was the realization that for every B-7 shot down, American factories would produce replacements faster than Japanese industry could replace lost fighters. In February 1943, Asahi Press published a comprehensive book titled Anatomy of the Enemy's Aircraft. The publication featured extensive analysis of captured Allied aircraft with special attention devoted to the B-7. Photographs showed every major component. Technical drawings illustrated critical systems. Specifications filled page after page. The book became required reading for Japanese aircraft engineers. Mitsubishi engineer Hisanojo Ozawa, designer of the K-21 and K-67 twin-engine bombers, contributed an article on the B-17 for the May 1942 issue of Koku Asahi, Asahi's aviation magazine. Ozawa's analysis proved revealing in what it acknowledged and what it carefully avoided stating directly. He noted that the B-17E represented modifications to a design that first flew in 1935, suggesting the aircraft was based on outdated concepts. Martin B-10S and Handley Page Hayfords of the same vintage had already been phased out of service, Ozawa observed. Yet he admitted that improvements had made the B-7 a first-line combat aircraft and that the original design had been extremely good. Another Japanese aviation expert, Shizu Kikahara, designer of the four-engine Kawanishi H-8K flying boat, examined the captured B-17S and commented on what he found most impressive. The American engineers have perfected the subsystems of this bomber to such a degree that a minimum of controls are needed in the cockpit. He wrote, "The simplicity of the cockpit arrangement, considering the plane size, demonstrated sophisticated systems integration." What these published analyses carefully avoided, stating explicitly, was the most disturbing conclusion. The B-7's construction methods represented a level of industrial organization that Japanese factories could not match. The aircraft was not superior because of better aerodynamic design or more powerful engines. It was superior because American industry could produce it in quantities that would overwhelm Japanese air defenses through sheer numbers. The examination revealed the B-7's construction in extensive detail. Wing panels were stamped from dies rather than hand-formed over wooden forms. This required massive hydraulic presses and precision dies costing fortunes to produce. But once those dies existed, workers could stamp panels by the hundreds per day. Control surfaces showed identical forming. Every aileron, elevator, and rudder section appeared to have been produced from master tooling rather than individually crafted. The main wing spars, critical structural members carrying flight loads, were machined on automated equipment. Drilling patterns matched exactly across multiple aircraft. Any wing rib from one bomber would fit precisely into another aircraft of the same model. The landing gear demonstrated automated precision machining. Main struts were forged components, heat-treated and machined on automated lathes. Actuating mechanisms consisted of hardened components machined to identical specifications. In early 1944, one of the captured B-17 Easy was damaged beyond repair in a ground accident. During takeoff from Fosse Airfield, the aircraft was caught in an unexpected crosswind. Its right wing collided with a parked Ki-49 bomber. Both aircraft were destroyed. The incident provided an opportunity for destructive examination. Engineers could cut into the damaged wing structure to examine construction details not visible in intact aircraft. By cutting through the wing skin and structure, engineers could measure rivet installation with precision. Hundreds of rivets were measured. Diameter variation proved minimal, less than 20,000 of an inch. Installation depth varied by less than 1/10,000th of an inch. Such consistency across thousands of rivets was impossible to achieve through hand riveting. The aircraft had clearly been assembled using automated or semi-automated riveting equipment. The implications extended beyond the immediate question of how one aircraft was built. If American factories could produce B-7 with this level of consistency, they could produce them rapidly. If parts were truly interchangeable, field maintenance became dramatically simpler. If workers needed less skill because precision was built into the tooling rather than the craftsman, production could scale up quickly by training new workers. Japanese aircraft production faced exactly the opposite situation. Skilled craftsmen remained in short supply. Training new workers to the required skill levels took years. Increasing production meant finding and training more skilled workers, not simply adding more assembly stations. In May 1945, American photographic reconnaissance over Tachikawa airfield captured images that puzzled intelligence analysts. Clearly visible was what appeared to be a new type of Japanese 4INE bomber or transport. Analysts estimated the aircraft's wingspan at approximately 104 feet. The mysterious aircraft was designated Tachikawa 104 based on the estimated wingspan and its location. As weeks passed without additional information, speculation grew about Japan's apparent development of a new heavy aircraft. Despite intensive bombing of Japanese aircraft factories, none of the American analysts who examined the photographs suspected the truth. The mysterious aircraft was actually one of their own B-17E flying fortresses, still undergoing evaluation by Japanese engineers 4 years after its capture. The actual wingspan of the B-17 measured 103 feet 9 inches, making the American intelligence estimate remarkably accurate. The extensive evaluation of captured B-7s had surprisingly little impact on Japanese bomber design. Japan attempted to copy the Douglas DC-4E transport as the Nakajima G5N bomber, but its other 4INE land-based bomber, the Nakajima G8N, which entered production near the war's end, used more advanced structural designs that gained nothing from the B-7's airframe engineering. There is evidence, however, that components and systems from the B-17 influenced later Japanese aircraft. Most notable were attempts to perfect turbo superchargers for high-altitude performance. Several advanced Japanese designs, including the Army's Tachikawa K-74, Mitsubishi Ki-83 and Nakajima K-87, as well as the Navy's G8N and Mitsubishi J2M, failed to reach their full potential mainly because Japan could not successfully implement turbo supercharger technology. The problem was not understanding the technology. Japanese engineers who examined the B-17 understood how turbo superchargers worked. The problem was manufacturing. Turbo superchargers required high-temperature alloys and precision manufacturing that Japanese industry could not consistently produce. Even when experimental units were built, they proved unreliable. The same manufacturing limitations that prevented mass production of standardized B-17 components prevented development of advanced engine technologies. By 1944, the cumulative evidence from examining captured American aircraft had led thoughtful Japanese engineers to sobering conclusions about relative industrial capabilities. American aircraft production reached 96,000 aircraft in 1944. Japan struggled to produce 28,000, but the disparity in numbers understated the real gap. American aircraft consisted of thousands of precisely manufactured interchangeable parts. They could be maintained by mechanics with basic training using standardized replacement components. They could be repaired in the field quickly and returned to service. Japanese aircraft remained craftsman-built machines requiring skilled technicians for maintenance, specialized parts for repairs and constant adjustment to remain operational. Each American aircraft represented greater actual combat capability because it could be kept flying with less effort and fewer specialized resources. The production system that enabled this output was visible in the B-17's construction. Boeing's Plant 2 in Seattle had produced 6,981 B-17 by the time production ended in April 1945. At peak production, 16 complete B-17 rolled off the assembly line every day. Douglas Aircraft in Long Beach produced 3,000 B-17s between July 1942 and July 1945. Lougheed Vega in Burbank built 2,750 B-7s between August 1942 and August 1945. Total B-7 production reached 12,731 aircraft from all three manufacturers. The Japanese engineers examining captured B-17s in 1943 and 1944 had no access to these production statistics, but they could calculate approximate production rates based on observed serial numbers and construction dates documented in the aircraft. The mathematics proved devastating. If American factories could build B-7s with such precision and consistency, they could build them rapidly. If they could build heavy bombers this quickly, their production of fighters and other aircraft must be proportionally greater. Japan had entered a war of industrial attrition against an opponent with 10 or 20 times its manufacturing capacity. The strategic bombing campaign against Japan's aircraft industry, which intensified in 1944, destroyed any remaining hope for matching American production. Boeing B-29 Superfortresses, the B-7's larger and more advanced successor, appeared over Japan in formations that Japanese defenses could not stop. Each raid destroyed production capacity that could not be replaced. The Nakajima plant at Musashino, the Mitsubishi facilities at Nagoya, the Kawasaki factories, all suffered severe damage from precision bombing. An earthquake in January 1945 compounded the damage to Mitsubishi's supplier network. The combination of bombing and earthquake collapsed Japanese aircraft production. By early 1945, monthly output had fallen from over 2,500 airframes in May 1944 to barely 1,500. The decline continued through the final months of the war. After Japan's surrender in August 1945, the United States Strategic Bombing Survey conducted comprehensive examinations of Japanese war production. Teams of American engineers toured Japanese aircraft factories, documenting production methods and assessing industrial capabilities. What they found confirmed the conclusions that perceptive Japanese engineers had reached through examining captured B-17s. Japanese aircraft production relied heavily on skilled manual labor. Standardization remained limited. Interchangeable parts were more aspiration than reality across much of the industry. Subcontracting networks provided components, but quality control and dimensional consistency proved problematic. American engineers touring the Mitsubishi facilities at Nagoya observed skilled craftsmen hand-forming aluminum panels that would have been die-stamped in American factories. Manual riveting predominated where American factories used automated riveters. Individual fitting and adjustment were common where American factories used precision-manufactured interchangeable parts. The survey concluded that Japanese aircraft factories had been organized appropriately for producing hundreds of aircraft. American factories had been organized for producing hundreds of thousands. No amount of determination or skill could overcome that fundamental disparity in industrial organization. The captured B-17s examined at Takiwa from 1943 through 1945 were destroyed in the war's final months, either by American bombing or by Japanese authorities, eliminating evidence. But the lessons those aircraft taught survived in the minds of the engineers who had studied them so carefully. In the decades following the war, Japanese industry underwent a transformation more profound than anything attempted during wartime. Engineers who had examined American aircraft and documented American production methods brought those lessons to Japan's post-war reconstruction. They understood that matching American industrial capability required not just copying American products, but implementing American production systems. The transformation required 20 years. Japanese factories that had relied on skilled craftsmen reorganized around precision machinery and automated processes. Industries that had valued individual craftsmanship learned to value systematic efficiency. Manufacturing that had been organized as collections of skilled workers evolved into integrated production systems. By the mid-1960s, Japanese factories were producing automobiles and electronics using automated production methods comparable to American factories. By the 1970s, Japanese manufacturers had refined those methods, developing production systems like Toyota's just-in-time manufacturing that improved on American mass production techniques. The skilled craftsmen remained valued in Japanese industry, but their role had changed. Instead of individually crafting products, they designed production systems and tooling that enabled less skilled workers to produce precisely manufactured products at scale. The precision that had once come from the craftsman's skill now came from the precision of the tooling and equipment. Companies like Toyota, Sony, and Honda became global leaders by combining Japanese attention to detail with American systematic production methods. The quality that Japanese products became known for resulted from production systems designed to build quality into the process, rather than relying on skilled workers to individually craft quality products. In the 1980s, when American manufacturers faced intense competition from Japanese imports, American engineers toured Japanese factories to learn efficiency techniques. The irony was not lost on those who remembered the wartime examination of captured American aircraft. The story of Japanese engineers examining captured B-7 bombers became a case study in Japanese engineering schools. It illustrated how examining an opponent's products could reveal fundamental principles of industrial organization. It demonstrated that success required understanding not just what competitors produced, but how they produced it. The captured B-17s had taught Japanese engineers that modern industrial warfare was won not by superior craftsmanship, but by superior production systems, not by building better individual aircraft, but by building adequate aircraft in overwhelming numbers. Not by skilled workers, but by systematic processes that enabled less skilled workers to produce precisely manufactured products rapidly. Those lessons learned through careful examination of enemy equipment during wartime became the foundation for Japan's post-war industrial success. The transformation of Japanese manufacturing from craftsman-based production to systematic mass production represented the final victory of the principles embodied in those captured B-7s examined at Tachikawa. The engineers who had measured rivets and documented production methods in 1943 and 1944 became the architects of Japan's industrial rebirth. They had learned by examining aluminum and machinery that modern industry belonged not to those with the most skilled workers but to those with the most effective production systems. In manufacturing engineering courses today, the story serves as a case study in how examining competitors' products can reveal invisible systems and methodologies. It demonstrates that understanding an opponent's methods matters more than copying their designs. It shows that the principles of production ultimately determine the outcomes of industrial competitions. The Boeing B-17 Flying Fortress dropped 640,000 tons of bombs during World War II. It earned its reputation as one of history's most effective heavy bombers through combat operations in every theater. But perhaps its most important contribution to history was not the missions it flew, but the lessons it taught when Japanese engineers examined captured examples. Those engineers discovered that American industrial power came not from superior materials or better designs, but from superior organization of the manufacturing process. They learned that standardization, precision tooling, interchangeable parts, and systematic production methods could achieve what skilled craftsmanship alone could not. The ability to produce complex machines rapidly and in quantities limited only by available resources. The captured B-7s examined at Tachikawa are gone, destroyed more than 70 years ago. But the lessons they taught transformed Japanese industry and influenced manufacturing worldwide. Engineers and manufacturers globally learned that mass production and quality were not opposites but complementary aspects of properly organized industrial systems. The story that began in February 1942 on a muddy Java airfield with a damaged Boeing B-17E awaiting capture by advancing Japanese forces ended decades later with Japan and America as partners in advancing manufacturing technology. The examination of those captured bombers had taught Japanese engineers that their defeat was inevitable. More importantly, it taught them why, and in understanding why, they learned how to ensure that industrial inadequacy would never again limit Japan's capabilities. The Boeing B-17 Flying Fortress served as teacher to its enemies, and they learned the lesson well.